Hello, so in this chapter we look at techniques for computing limits. Now, in the previous video I kind of used the techniques in that chapter where we looked at the left and the right, and then we looked at several examples of how we can rewrite expressions and use graphs and things like that. So just to kind of give you a sort of idea of like what this chapter does is it establishes that you are able to say, for example, um, like let's say for example, like if you have that the limit of f of x as x approaches 1 is equal to 5, but then let's say that you have similarly that the limit as x approaches 1 for g of x is equal to 2. So let's say, for example, that if you had that you were taking the limit as x approaches 1 for 2 times f of x minus g of x all divided by, let's say, uh, g of x plus 1. Well, what this chapter establishes is that essentially you have all these different rules. Let's say that that's squared. It has like all these different rules that you can apply the limit operator. So like for example, you have that can become the limit as x approaches 1 for f of x, but just take out the 2 minus the limit as x approaches 1 for g of x, and then all of this is divided by um, the limit as x approaches 1 for g of x squared plus, well, we have that you're taking the limit as x approaches 1 for the value 1. So essentially I'm just applying the limit operator to the numerator, then furthermore just distributing the different rules. So accordingly this would be like 2 times 5 plus 2, not plus 2, minus 2, right? Okay, so that should be minus 2. And then we have that this is going to be divided by, well, you have 2 squared plus 1. So that's going to be 10 minus 2 divided by 4 plus 1, which is equal to 8 over 5. So that gives you that the limit of that function, or that expression, sorry, is 8/5. So more or less, the chapter is more or less just telling you that it works out the same as you would think it is. Like the limit of a constant times a function, the limit of the sum of two functions, the limit of a function squared, and so on. So I'd recommend that you go ahead and you just read through the limit laws, and then you just look at how they can be applied on a case-by-case basis. Because sometimes it may not be, the limit may not exist anyways. So what I plan to do with this one, with this this section, is to look at some more problems. Um, so really, essentially, this is more or less just a repeat of the previous section. So we'll just look at if we want to find the limit as x approaches 4 for 1 over x minus 1/4 divided by x minus 4. Okay, so let's do it like this. X minus 4. Okay, so what we'll do here is look at how we can basically either add both of the two terms using common denominator, or we can actually just simplify it, whichever the case is. But it looks like, yeah, the easiest way to do this is to probably just multiply it by 4x. So 4x is the common denominator. So we're going to multiply by 4x. And what this is going to do when you distribute, you end up with 4 minus x. Okay, so you end up with 4 minus x divided by x minus 4 times 4x. But notice that basically these two are opposites of each other. So these cancels out and it reduces down to a -1. So this equals to the limit as x approaches 4 for -1 over 4x. Now if you take the limit to the denominator, you're basically going to get that it's going to give you equals, so you have the limit as x approaches 4 for -1 divided by the limit, well, we'll just say 4 times the limit as x approaches 4 for x. But you learn that basically this just gives you -1 because it doesn't depend on it. Then you have 4 times 4, and then that equals to -1 over 16. So the limit is -1/16. Now you could have probably just plugged in 4 directly and then just be done with it, which accordingly those limit laws that you'll need to look at in 2.3, they do summarize that you can actually do that, where you can just substitute the 4 and then it gives you the exact same thing. Now there's another example that I'd like to do before I move on to some other types of limits. So let's say that you want to find the limit as h tends to 0 for the square root of 16 plus h minus 4 divided by h, and that's it. So actually 0, let me just double check this. I'm pretty sure that it should be, yeah, that's fine. So if I plug in 0, I notice that basically I just get 0 over 0, which is indeterminate. So we want to basically just figure out like how we can reduce this. So let's say that we go ahead and we just look at the square root of 16 plus h minus 4, all divided by h. Now multiply by the conjugate in this case, where you have 16 plus h plus 4, and divide all of this by the square root of 16 plus h plus 4. And this gives you the following. It gives you 16 plus h minus 16 divided by h times the square root of 16 plus h plus 4. And then we notice that the 16s, that they will cancel out. And we notice also that the h will cancel out too. So essentially this simplifies down to the following: 1 divided by the square root of 16 plus h plus 4. So what that tells us is that we're basically just taking the limit as h approaches 0 for, okay, so let's just write the square root of 16 plus h minus 4, all divided by h, is equal to the limit as h approaches 0 for 1 divided by 16 plus h plus 4. Now I want to basically just go ahead and apply those limit laws again, just so that you can kind of see how that works. because basically we have that it's going to be such that you have the limit as h approaches 0 for 1 divided by, okay, so accordingly this limit operator can be applied on the interior. So you have the limit as h approaches 0 for 16 plus h, and then you have plus the limit, so we'll just move this over here, the limit as h approaches 0 for just 4. Now, in class I usually say that I will only do the limit laws, so these are the limit laws that I'm applying to the numerator and denominator. I only do this really just like once or twice. Then after that, I just say it's pretty clear that you just plug in 0 and then that's it. So this will be 1 divided by, okay, so limit as h approaches 0, that's just 16, so that's just root 16. It's almost like adding extra steps. So you end up with 1 divided by 4 plus 4, which is actually just equal to 1/8. So the limit is just 1/8. And again, yeah, you could have just plugged in 4 once you reduced it, and then that's it. Like, not 4, 0. And then you would have reduced it to just 1/8. Now, what we can look at next from this section, we can look at, like, for example, like some trigonometric limits. So one thing that that you'll see, for example, is that okay, so first off, let's just establish this. So based on the squeezing theorem, we have that -1 is less than or equal to sine of x over x, and that this is less than or equal to 1. Okay, so essentially what we do have here is that if we take the limit as x approaches 0 for sine of x over x, this is going to equal to, let's see, actually this lower bound should be cosine of x. Okay, so this should be cosine of x. Okay, so basically we have that this is going to be equal to 1, but the question becomes how. So if you take the limit as x approaches 0 for cosine of x, this is equal to 1. And you also have that the limit as x approaches 0 for 1, well, that's just equal to 1. So that means that by squeezing theorem, we have that the limit as x approaches 0 for sine of x divided by x is equal to 1. I would say, you know, if you want to show using a table, then basically just try using a table. That's another way that you can do it. But the main thing though is that we have an established trigonometric limit that you will need moving forward into the class. So the next thing that I can do is basically say, for example, that I want to find the limit as x approaches 0 for 1 minus cosine of x divided by x. Well, the way of which that I would do this is that I would basically just say, well, first off, I know that 1 minus cosine of x, if I multiply by a conjugate, like 1 plus cosine of x divided by 1 plus cosine of x, this is going to give me 1 minus cosine squared x, which is divided by the sum, or the 1 plus the cosine of x. Now, we know that 1 minus cosine squared x is sine squared x. So that's just sine of sine squared x divided by x. And then we have 1 plus cosine of x. Now, this is where it gets a little tricky. Accordingly, you just learned that you can multiply two limits. So you have sine of x over x multiplied by sine of x divided by 1 plus cosine of x. So what this does is it tells you that you can basically just take the limit of this expression. So you have the limit as x approaches 0 of, okay, so you have sine of x over x multiplied by sine of x over 1 plus cosine of x. Well, you know that this is equal to the limit as x approaches 0 of sine of x divided by x multiplied by the limit as x approaches 0 of sine of x over 1 plus cosine of x. Now, interestingly enough, we have that this is going to equal to 1. So we have 1 multiplied by, well, if you take the limit of that, that's going to be sine of 0. But sine of 0 is 0. Divided by 1 plus cosine of 0, which is 1. But notice that this is just 0. So we have that that's just going to equal to 0 in this case, because we just used the established limit. So thus, we have that the limit as x approaches 0 of 1 minus cosine of x divided by x, that this is just going to equal to 0. Okay, so this is actually a very important trigonometric limit as well, because once we look at derivatives of trigonometric functions, we're actually going to need these two limits, the sine of x over x, and then also the 1 minus cosine of x. Now, I'm just going to do like a really easy example before I move on. So let's say that I want to find the limit as x approaches 0 for, let's say, like sine of 2x divided by, okay, so let's see, sine of 2x divided by, I'm just going to do x, okay, so this is going to be x. Now, accordingly, what you do have is that if you plug in 0, you end up with 0 over 0, which doesn't work out. So, accordingly, the thing that you have to realize is that the coefficient x has to match. So, in this case, there needs to be a 2 here, which there's not. So, in that case, like you would have to say, okay, so how do I change this so that it matches 2x and 2x? So what you can do is the following. You could probably just say that you can rewrite this as the limit. Okay, so the limit as x approaches 0 for sine of 2x divided by x, but multiplied by 2 over 2. What you're going to do is you're just going to borrow the 2 over here and then just rewrite it as 2 times the limit as x approaches 0 for sine of 2x divided by 2x. But the thing that you do know is that this is going to be 2 times that limit, which now you just use that property that says that sine of any coefficient x divided by the coefficient x is going to be 1. So that equals to 2. So in this case, like we have that that's equal to just 2. Now, I would recommend that you do try another trigonometric limit. So, like for example, try the limit as x approaches 0 for tangent of 2x divided by x and see what you get. If you get the same thing, then, okay. But if not, then, just use those techniques. And I'll just say that, you just have to change this tangent to sine over cosine. Now, I don't think that maybe, like, yes, if you would have expanded this using the double angle identity, it would have worked out the same way too. So if you want to try using the double angle identity for this one, then yeah, you can actually, and it'll give you like the same thing. Um, the other thing of which that I want to do for this question or for this chapter at least is another example because I mean most of the problems that they have in the textbook we've already kind of like established that yeah you can take the limit of the function as you know like just using algebra. So let me go ahead and just look at using some cosine. I'm sorry, using pinching theorem. So let's look at the following question where we have that we want to find the limit. Okay, so we want to find, yeah, so let's go ahead and find the limit for, okay, so we're just going to find the limit as x tends to 0 for cosine of x. Now, note that basically uh, the material basically implies that you can technically just plug in 0 and just be done with it, like you just have 1. But you do have that there's a condition that you have 1 minus x squared over 2, I believe, that's going to be less than or equal to cosine of x, and that's less than or equal to 1. Now, okay, so, and the reason that we can't use technically that cosine is bounded by -1 and 1 is because that kind of contradicts, sort of, in a way, like if you try to use that inequality. So that one won't really work. Like if you're using cosine is bounded by -1 and 1, that if you approach 0, that it gives you 1, but that doesn't work out. So that's why, like, most likely um, we're going to try to use this one. So if we go ahead and we use that, we need to find the limit as x approaches 0 for the lower bound for 1 minus x squared divided by 2. Well, we just learned that basically you can apply the limit operator to both of these two, but in either case you're just going to get 1. But if you do the limit of the upper bound according to squeeze theorem, you have that that's also going to be 1. Now basically this gives us that by squeezing theorem that the limit as x approaches 0 of cosine of x, that equals to 1. So in that case, like, that's it. Now if you wanted to, let's say for example the graphing calculator, or just a calculator for instance, you can do that. You can say like y equals cosine of x, and then you have 1, or you could plug in y equals 1, for example. Okay, so that's y equals 1, and then you have y equals 1 minus x squared. Okay, but it's 1 minus. Okay, so let's see. Oh, no, it's x squared. Yeah, it's supposed to be like a parabola. So x squared, and then that's divided by 2. Okay, there we go. So yeah, these are kind of like weird numbers. So we have that the green is the cosine function. So we can kind of see that if we get really close to here, that basically you have that the green graph, it gets kind of like squeezed in here at 1. So we have that if we approach 0, we just get 1. But that's the value for this one. Okay, so just be careful with that. But if I remove it and I remove it and then I just do that, I can see that, yeah, okay, that's just going to be 1. But basically, squeezing theorem is essentially just establishing that you can bound it below and above, and then just use that so that you can figure out that that's going to be just 1 for the limit. Okay, so um, that's going to be it for this section. So mostly you were just having to just redo most of the computations for finding limits. If you have the time, maybe go ahead and show that if you have that you're going to take the limit of, let's say, the limit as x approaches 0 for yeah, for x times sine of 1 over x, that equals to 0, um, then yeah, that's going to be pretty much like more or less the exact same thing if you think about it. But essentially, you're going to have to find the bounds, which you already technically know the bounds for sine of 1 over x from the textbook. It's going to be less than the absolute value of x, and that's less than the absolute value of, well, minus the absolute value of x. And that's where you're going to put the x right there. So that tells you that you can apply the squeezing theorem by using that bottom condition. Okay.